Okay. So an example of a kind of page 115 is an example of the 0 to the n, 1 to the n PDA. And page 116 is that more subtle a to the I, b to the j, c to the k with ijk greater than or equal to 0 and either I equal to j or I equal to k. So it's a union of two different ones. Well, and if you look at that, it's got lots of epsilon moves to take it down the two different paths. And the one lower down on the page gives another recognizing WWR. And none of these have accompanying CFGs with them. So what you would have to do, the process to build that PDA is to just look at the language and start trying to figure out states, kind of ad hoc, whatever you can figure out along the way. So as an alternative to that, that's not in the book, I give you a generic PDA that will work for any CFG. So if you can just put the language into the CFG, then you can make a machine that will recognize that language. So that's the motivation. Ease of implementing the PDA. Because it's very straightforward. So let's see. We already do. Well, I'm thinking of CFG. Our generic PDA only needs 3 states. One of them being the accept state. And so this is always going to be the same. What are we going to do? We're pushing a $ onto the stack initially before we see anything. Empty string move, going to don't care, and put the $, and that's the bottom of the stack marker, and we put the start non-terminal onto the stack. So those are going to, as soon as we turn the machine on, we're going to jump to Q1, sorry, and put whatever the start symbol is. We just routinely use S, right? And then in order to get to the accept state, we're always going to put an empty string move that says if I'm at the $ left, just pop that off and empty the stack. Okay, so any questions on how, or the purpose, the why of that? And that's straightforward, just kind of giving that to you. It's just to initialize the stack and get the stack readied up, and then as soon as we can, when we get to the bottom of the stack, we're going to try to jump to the accept state. And what's the other condition we need? I'm sure there'll be a question on the exam. the third condition, we've got an empty stack, got an accept state, and what else has to be true? Yeah, we've used all the input string, right? So if there's any letters left over, we can, well, if there's no way to use them up, then it fails, right? There's no way to accept. And we're counting on what the non-deterministic nature to pick the right rule, right? So we go back to the non-deterministic idea is that any, if there exists a path that can move us along and accept only strings that are within the language defined by the CFG, then it will find it. So, when it, this is always kind of lurking out there. And if the, if you somehow get to the empty stack and you're not quite done, and there's more processing you could do, it would try this and then say, oops, didn't use up the input, and so it come back and wait and try something else as long as there's something else to try. So for our CFG, let's try this. The set of strings. This is definitely not regular because you have to count up the A's and make sure there's a matching number of B's, which a DFA cannot do. So what would a regular, like what I just said, what would a CFG look like that would accept this? Yeah, the way we typically, sort of the default way to build something like that in one piece is to this assumes, let's see. Yeah, let's see. We can do it for n greater than or equal to 0, and then we can just go to an empty, right? So the variation would be, if it has to be greater than 0, then we would put n of 1, AAB, as the stop the repetition, stop the recursion. Right? This will work for 0. And so this is a very simple when there's only one non-terminal. Let's see. Okay. Duplicate it. Let's just do this. So for an easy example, we can change that and control something else here. We only have two. What we're looking for is transitions on Q1 back to itself. And what the whole idea, the purpose of those transitions is we've got an input string over here. And we've got this set up, initialized. We've got this set up, so we're looking at the first character. And now we want to be able to, we've already jumped to Q1, so we want to look at the transition labels that we need to put on that guy so that he will properly put stuff on the stack, take stuff off the stack, all so that it will count up the A's and the B's and match them up. So the kind of straightforward don't use the CFG method would try to push A's, push every time you see an A, push it on the stack, and every time you see a B, pop 2 A's off the stack or something like that. Rather than doing that logic and additional states that we're required to do that, we'll just manage it by using the CFG rules. And those are going to look like for each, for non-terminal, we put in a epsilon that says if it is at the top of the stack, replace it with its right-hand rule, and every time we want to do that for each of the rules. So the easy one is replace it with the empty string. The other epsilon on an S is to push, and here's kind of the, we want to put that on top of the stack so that we push. So those are the only two ones. So actually those we would write. These are the transitions, labels. Got S on top of the stack and push its right hand side on there. That's just repeating that. And then for each terminal, you put a rule of the form. If I see that in the input and it's on top of the stack, top it off. You can do that. There's just two terminals here. If I see an A is on top, top it off. If I see a B, B's on top it off. And that's it. So instead of having to come up with a series of states similar, well, I guess simple one, we'd have to expand a little bit on like page 115, figure 215. But we, let's see, can we do? Maybe we'll do that. All right. So that's it. We did the terminals and we did the non-terminals. There's only one or two rules. So now we can I got a little bit of room. I'm going to just move this. So here's my input. Right. So we'll try it with one that's in the language. And so we don't have to try every single possibility. So a bad choice at this point would be what, applying this epsilon rule and popping the S off, which would immediately cause us to jump down here. We should say, yay, we emptied the stack, we've got an accept state, and oops, we didn't use something in the input. So, so that would fail. But now it says, well, let's see, is there something else we can try? So this would, in the most naive way, go try every single possible combination. It can't do, or it could do this. Well, we'd say, oh, I've got an A. This might work. Is there an A on top of the stack? No. So I can't do this There's no B, so I can't do that. That didn't get me very far. But now I can replace without consuming input. So empty string move, I can push, replace the S with that. So notice how even though, I mean, we're bunching a lot of work in, but it's really, hopefully, you're getting the impression that by using the convenience of building CFG, making it look nice, easy, readable, we don't have to explicitly push the individual A's and B's on here and keep count of them. I mean, it's actually happening, but through a more understandable mechanism. So now, what would happen? Now we got an A input and an A on top of the stack. We would pop the A off and consume that. Okay, it got consumed. Another A, so we can do that again. Match A matches A, pop it off. We're looking at the third A, and nope, that's not on top of the stack. Our choices are to pop off this S, and now with our human looking ahead here, if I pop that S off with this rule, then I'd have a B on top of the stack, but I don't have a B that would move me ahead, so that would fail, right? So let's try. The only other thing I can do is that same move, push stuff back on. So B, B. We push that right-hand side on. Now I'm back in business. Match the A. Pop it off. Move ahead. Same thing again. Pop that off. And now I advance, I'm looking at a B. So there's not a B on top of the stack, so I can't do that. I'm not looking at an A. Because I can see a little ways ahead, I won't push another B on here because I've got two B's. Two B's are not two B's. And I'm looking at this not as the machine. I see, oh, okay, I've got two B's, here. So a smart move is probably to take the S off, right? So how would the machine do it? It would try taking it. It would try pushing another one on and fail. When it pushed another couple of A's on there, go, oops, no, don't match A's. I've got a B, and so it'd have to come back down, taking the S off, taking the B away, and matching the last B, which finally gets us there. Yay! We got all the way through the input stream. Now we'd have the dollar sign. Now it takes the expressway over to Q2 and have success. Great success. Really good success. Yeah. Okay. And so you should understand both how to get from here to here. All right, so I would give you on a problem just like on the sample problem, I would give you this, the basic generic framework, I guess, for PDA, and then I'll ask you to fill in appropriate rules. So you gotta have, you gotta memorize, if you want to call it that. Work with, look at the book, and look at what we've done on the board, and know how to make rules. So non-terminal always has an epsilon and tries to push right hand side. The terminals always match the terminal and pop them off if they match. So two different things we can do is push a right hand side rule or match a terminal and pop it off. Those are the only two actions. But we should look at a fail mode here. An easy fail mode would be what? There's an extra B hanging off the end. So we got all the way to here. We zoom over to Q2 and oops, we got an extra B. We didn't use up the input, so we'd have to backtrack if there was another choice. It turns out, the only other, we probably would have used up all our options for this because there's so few of them. So we would conclude that that was not acceptable. The other failure would be what if, we could lose an A, we could have only 3 A's, right? And then where would we get stuck? When we went to the second, we pushed 2 A's on, pushed 2 more A's on. We have the third A would pop off that guy, and then we'd be on a B if we're missing an A here. We would we'd be looking at a B, and we'd have an A on top of the stack, and nothing we could do. Okay, so I just took the B off. If we're short of B, then our joyful trip would end here with used up input, a B on top of the stack. We couldn't get out of Q1 at that point because we don't have the dollar sign. So, all right, any questions on the? There will be a question of this nature on your exam. So. Speak now or forever hold your peace. Unless you think of it late and then send me an email or something, and I'll say, look at the video. Right? Looks good? Yeah.
Can you do like a parse tree example?
Yeah, let's see. Well, let's just reuse perfectly good CFG, repurposing, recycle, reuse, right? And use up any extra marker. Causes all kinds of diseases in an instructor. Thought you were maybe falling asleep. Okay, so let's string. Let's do a derivation first. That's always a good place to start. We always start with S, and let's try to get to that. We know we can get there. So we would replace S with a SB and do that again. right? So we're filling in from the middle here. We're stuffing AASB in that slot. So these are the original AAs over here, and these are the new ones we just added. And that was it. So then we just go to, that would be, yeah, we made it. Right, so the S gets replaced with an empty. So to do a parse tree of that, at each point we want the children of each node in the parse tree are the characters, the symbols that came out of the rule that we applied. So we're going to get, that's a child, it went to an S here, and this was the child of the original one. So we're filling in the middle here. This S gave us A, and that B. We have to show that middle S went to empty string. So if we have multiple, I guess what we're not looking at is the possibility of more than one non-terminal, in which case we can do a leftmost derivation or a rightmost derivation. Leftmost well, we can do a random one if we wanted, but let's just any number of A's, any number of B's, or just an AA. So now we have more than one non-terminal, and we can either do it, derive just sure, we can make an equal number. Now it's making it AAABD. So we go S, we replace with AB. Now if we do leftmost, we're always going to take the left-hand symbol to replace. So we replace that A with A, A, and finally. Right, and continuing, let's see. Oops. So we replace the B with a little b, big B, then get. So at each step, when we had a choice, we took the leftmost non-terminal to replace. Another perfectly good derivation would be, this is leftmost. Every time you have a choice of terminal, not of non-terminal, you pick the left one. The rightmost is going to do the opposite, and it only changes the sequence of choices, but not the rule applied. So we'll replace now the B first. That would give us, keeps our big A, will be big B. Again, rightmost, big A. Get rid of that. And then we would apply the A rules. And finally, so. And it would, unless you were asked for the leftmost or rightmost, you could randomly pick which one you replace and still get a good derivation. Right? What's the purpose of leftmost, rightmost? Just to make it easier to follow what's happening. And then getting, now, is there going to be two different parse trees? For these two? Well, the parse tree shows the rules, and these actually apply the same rules. The parse tree does not show the sequence. So we would expect one parse tree will work for both of these because we applied just the simple rules. There were no choices here. So we'd start with S, and children are just going to be the immediate characters, the symbols that follow it. And we went down so, and again, so, and the B, gives the B, and the B. That's it. So in fact, the derivation shows that the leftmost one says I substituted for this A first, get the first A with that, and so I should be able to trace through the derivation from the parse tree and see, okay, the next one we applied the A, then did A, and the third on the leftmost did the A, just goes directly to A. And similarly, the B. And it doesn't matter the sequence, right? So on the rightmost, we went down this side of the parse tree, same parse tree, but we just applied the rules from the right side before we did the left side. Okay, anything else? An exam nature. None of what we talk about today, new stuff, will be on the exam. Yeah, looks good. So if you don't have anything, we introduced Turing machines a little bit last time. The introduction, the first Turing machine that, let's see, we talked a little bit about Turing and Turing test for AI. Do I remember Turing's idea?
Was about communication, right? You couldn't tell
Right.
that you were communicating.
Right. Yeah, yeah. So the Church-Turing thesis, a little separate. Church-Turing thesis says the Turing machine is as powerful as what we normally think of as a computing machine, the equivalent of any machine, including the one in your PC or supercomputer. Essentially, if a Turing machine is a model that can do perhaps a lot slower anything that a modern computer can do. What's that? Yes, for mathematically provable reasons regarding the nature of computing. So it's kind of a thing to recognize, as far as we can tell right now, in the world of trying to solve algorithms, the Turing machine can. They might say, well, wait a minute, I can have a 20 million core computer, and that's got to be faster. That's got to be able to do more stuff, right? And the answer is, well, not really. With that infinite tape they can write symbols on, the Turing machine is actually could do that, but it'd be pretty slow while it was doing it. I'm sure we have a few minutes here at the end to yeah, you need to. Never mind. Yeah, there's some videos that show implementations of Turing machines, but say that for after the exam. And the Turing definition of intelligence, and separate thing, kind of pull that in because it's another part of the work that he did, and that is the idea that how do you know a machine is intelligent? If you could, and this is pretty rudimentary, thinking that there were no digital computers essentially, or the very, very earliest computers, right? They're looking into the way far ahead into like the 1980s and saying what would intelligence look like? And his postulate, his idea was, well, if I could sit at a keyboard and modernize it, sit it with a screen and type messages and have them answered back, I mean, kind of like your chat. If you could do a chat with a machine on the other end and you couldn't tell whether it was a machine or not, then that was his concept that if you could really do that, you'd have an intelligent machine. In a slight rebuke of that, how many of you have had any AI class? Okay. I mean, no natural language processing class. Okay. There was an interesting experiment that amazed college students. In 1966, a program developed called ELIZA, and it was able to, you could sit down and it would say, what would you like to talk about today? Or it was actually framed as a psychotherapist who would ask you questions about your difficulties and help you work through your problems. So it was set up without the students having, or the participants typing in, having full knowledge of whether they were talking to a computer or a person. But the it would start with, tell me about your problem. It was the opening cue. And you could type in, I'm having trouble with my girlfriend. And it would reply with, why do you think you're having problems with your girlfriend? Can you tell me more? Well, she gets mad at me. Why do you think she gets mad at you? And interestingly, people, this is 1966, so the Beatles had just arrived on shore. They were screaming for the Beatles, put in a little context. But people were getting convinced that they were actually talking to another person, and they felt like they were actually working out their problems. And what was actually, it was a computer, and the program was doing very rudimentary pattern matching of language. And it knew that they had done, so pre-research was, what does a psychotherapist conversation look like of that nature? I guess it's out of my field. Rogerian, based on a guy named Rogers, was an early psychotherapist, and he had a kind of a routine of how to talk to somebody and help them work through their problems. And so what they're able to do is do a pattern, look at, I believe there were 15 or 20 patterns of answers and responses, or questions and responses that you might get from somebody. And so it would look for those patterns, and you could, once you figured out what it was doing, you could put silly things in that would mess it up, and we'd come back with silly answers. But if you kind of took it at surface, at face value, typing in reasonable answers for it and not trying to trick it, people would get pretty convinced and actually feel better. The interesting side effect was they felt like better about that they talked about their problems. And the whole time it was just matching, I'm having trouble with blank, here's the pattern match, and the response will be, why do you think you are having trouble with blank? And so it would just go through and do some very clever pattern matches in some cases. But and it was touted as early, early artificial intelligence discussions were starting. They figured they'd have the whole language thing figured out by the late 1970s, about understanding natural language and being able to reproduce it. Took an additional 50 years or so to get Alexa to play your songs and videos for you. Um, but it was, yeah, you know, do we call that, it kind of started a debate about, is that artificial intelligence? Or is it, well, the lowest level, it's pattern matching, right? You're just flipping sentences around, looking for the subject or the verb, kind of in a very rudimentary way. And if it couldn't match anything that it knew about, it would say something like, well, tell me more. And it had 3 or 4 different prompts that would ask, basically invite the typist to put in more information and hopefully a pattern that could be pulled out. Anyway, but artificial intelligence kind of is part of the whole question of can a Turing machine do artificial intelligence? Or can you do artificial intelligence that isn't, or that is more powerful than a Turing machine? If a Turing machine is the limit,
The hypothesis. But it's a hypothesis.
yes. It's like, got a couple of those hypotheses that we can't prove that they're true, but we're pretty sure they must be. And we can't prove them false. Okay, the introductory example. I think I'll do an even simpler one. Suppose you had a tape on which you had encoded your input string. So here's the setup for the Turing machine. Is it's got a read-write head on it. And it can change state based on the symbol that's under, it's currently looking at, like a DFA. But it can also, then part of its transition, if you look at the examples, page 172, 173, you can, if you have a certain symbol, you can write what's like, read symbol, and you can write a symbol, and move left or right, all as part of a transition between states, right? So we have 2 states where if I see a 0, write a pound sign and move to the right or something like that. So for our perspective here, if I say move the tape to the left, it's going to go that way. It's not a crazy assumption, but just so we're using the same direction. So suppose I wanted to check is it in the language, 0 to the n, 1 to the n? Well, I could, suppose I had something like, let's see, the left to right. How could you move around that tape to tell whether, and let's put a dollar sign at each end so we know where we are. What would can you imagine what a program would look like? What would be the strategy, like the high level process that you would go through? Let's say you are, I'll move the head around because that's easier to move on the tape. So you start here, you're looking at a pound sign. And your objective, think of it the way I usually, my goal in talking about the Turing machines is to have you start to think programmatically rather than state machine wise. Because similar, just like what we did with the PDA, between CFGs and PDAs, these get really complicated. And actually your book follows after the first couple of examples to scare you off on page 172, 173 with the actual showing of the state machines. We are not going to focus primarily on those, but like on page 175, the author gives and 174 gives on input string W, for example. Scan the input from left to right to determine whether it is a member of A star, B star, C star. Reject if it isn't. Turn the head to the left-hand end of the tape. Cross off an A and move to the right. This is to do A to the I, B to the J, C to the K. And so it describes the same problem that we had with PDA, solved with PDA. And talks about it in terms of it's much easier to understand and understand the limits of the machine if we start thinking about, okay, so how could we, given that our string is somehow encoded on the tape like this with a dollar sign or pound sign at each end, how could we move around and match to see if there's an equal number of zeros and ones? Well, we might let's start here. Move right. Let's see. So I'm going to move to the right. If I see a 0, let's write a dollar sign over it. I keep saying dollar sign, I mean pound sign. We moved over 1. And now what should I do? Trying to see if there's a matching 1.
You need to move right until you see a 1.
I can move right till I see a 1, and then do what? Basically, cross it off, right? So inside, I sort of pseudocode it. So I can move right until I see a 1, but maybe I ran out of 1s. I'm going to hit the pound sign. So if I see a 1, let's write pound sign over it. And let's see what happens. So let's move left until, oh. And we're going to repeat. So that was this. So step one, move right. If we find a 0, write a pound. Move right until I see a 1 or a pound sign. If I see a 1, write the pound. If I see a pound, then we'll talk about the error. I'm still expecting a 1 if I just crossed off a 0. So let's see if we can put it in terms of, I moved right until I found a 0, crossed it off, moved right until I found a 1, crossed it off, and then let's go back to the left until I hit a pound sign. And then move right 1. So that would get us to move right till we get the pound sign, and then move left till we get the pound sign, and then move right 1. So we'd be sitting here. So in this case, we've gone through the process of matching 1, 0 to 1, 1. And then we can repeat. This is that. And we can repeat that until what happens? Well, I'm sitting here, I see a 0, I can mark it off. Move right until I see a 1, and mark it off. Move left until I see the pound sign, and move right 1. So then move back here. Then I see a 0, cross it off, move to the right, until I see a 1, cross it off, cross it off, move left until pound sign, which would move back here, move right, and that means I've used up all my 0s. I'm sitting on a pound sign, and I didn't expect any more 1s or anything. So if I cross them all, so that I end up sitting on the pound sign, then I must have, I went back across oops, I think did I go across more than one pound sign? I think I messed you up here. Because we started with the 0s and the 1s. We took off, I think what we actually want to do is experimenting. If we go end to end and go toward the middle, then we'll, I was moving, when I got to here and I wrote a pound sign, I said move left until get to a pound sign. Well, that wouldn't have gone over to here. That would have just stopped here. Let's do 1, adjustment. Let's move right until pound sign. Then go back left. And then if it's a 1, right? And then if it's already a pound, that's going to be the error. Now we can move left until pound sign, then move right 1. So this way, it's going to, just to summarize, we'd start over here, move right 1, cross off that 0, move all the way to the next pound sign, which is going to get the other end. You know that's the end of the string. Remove this 1 from the end of the string. Move all the way back to the pound sign, move right 1. If it's a 0, cross it off. If it's a 1, then we have a bad situation, right? It fails because when we move all the way to the left, we should see a 0, or when we get to the end, let's see what happens. We move to the right until we get to here, back up 1, it's a 1, so we're happy in that state. We can back up to the 0, or back up to the pound. If I see a 0, well, if I see a 1 here, it means we have a failure, it didn't match. So we have 0, we write that, move to this one, jump back, move here, move back to the pound, and if we have a pound on that move left, on the final move, we move back to the pound sign, which is first 1 jump, then we go right 1, and if it's a pound sign, that means we have success. So we have to put a couple of states in there to tell whether, basically the states in the Turing machine would tell us whether we are looking for whether we're backing up to look for a 0 or moving forward to look for a 1. And basically, this is a good example of the kind of processing that any Turing machine is going to do. It's basically shifting back and forth across, or moving the tape back and forth, and doing this kind of high level to visualize it, put it in some high level pseudocode like language so that we can see what it's doing and get the gist. So this is kind of the level of understanding that I want us to get to, is that we can propose a Turing machine. You give me the input, tell me what I'm going to check for, what the operation is, and I can come up with a way to have the tape maneuver back and forth until I can tell whether, in this case, whether it had an equal number of 1s and 0s. So we're not using a stack. The Turing machine itself does not have its own memory. It doesn't have a stack. Why would it need it? It's got an infinite tape, so it could, if you wanted a stack behavior, you could just put a symbol, move out 10,000 blocks and write a little special symbol that means start of the stack, and put a $sign out there, and then just use it, go out to the $sign, and then back up to push things onto the stack or look for a blank to find the end of the stack. So it doesn't need separate memory. It can just it can mark off if you want, right? Imagine you mark off different pieces of your infinite tape and just use them as memory however you want. So you could make this act like a PDA, for example. You put your, basically keep the tape as a stack and do exactly what we were doing with the PDA, getting a $sign and write symbols on the tape as if you're pushing them on the stack. Look at the one that is where you just left off, compare it to the input, if it matches the terminal, back up. And that can also all be done with state transitions, just like in the PDA. But now we've moved into, we don't have limitation on how we can access the memory. We don't have, we have memory that is boundless, and we can go anywhere we want and do anything we want with it. So it starts to, when you think about what the assembly language does in a real life computer, you start thinking, well, all those are simple instructions, moving data around, doing very simple math operations. We'll look at math operations next time we talk about Turing machines and show how in a kind of backwards, different way, we can do math with this thing. And the final kind of pulling the pieces together to kind of convince ourselves that it can work like a regular, like a real live computer, is bringing in the idea that we can make sort of subroutine jumps. We can make different parts on this tape. We got lots of room, so we can do anything we want. We can have implement things like addition, subtraction, all the things that you might put into a CPU logic unit. You can just kind of code those in. That's not going to be real simple. We might have lots of states, but we can do the same thing and convince ourselves that whatever computing we can do on our PCs or any supercomputer for that matter, mainframe, we can do that with a lowly little Turing machine. All right. Let's call it a night. Exam will be Wednesday. Full class period to take it. Let's see, anything special. One sheet of paper of notes, no calculators needed, no electronic devices. One page, 8.5 by 11, one-sided notes. Closed book, closed notes.